So hey everybody, welcome back from your spring break. As you know, we're going fully online for the foreseeable future here at Chaffey College. So that means the format of the lectures is changing a little bit. I'm going to be creating these online lecture videos for you to consume through YouTube. And this is the first one that I'm making for Physics 46. So before we get started, just want to say I hope everyone out there is staying safe and healthy. And thanks for bearing with us through these changes. I know it's changing rapidly for a lot of you. And we're probably going to have a few technical kinks here and there as we make these videos, so just try to bear with me through that. But I do want to remind you that all of the lecture slides that I'm going to go off of here are the same ones that I've been using for the entirety of the semester so far. And you always have these available on Canvas. So if there's something that looks a little grainy, you can't quite make it out in the video, again, just follow along to those lecture slides that I posted to Canvas. Also, I'm going to be posting some additional content to Canvas, my own handwritten notes. This is what I use when I go to the board to do a derivation or to work out a problem. I'm going to scan these, upload these to Canvas, so you'll have those available too as you watch the lecture videos. But as far as how you approach the lecture videos, I would encourage you to treat this just like an in-person class. So take notes as you watch the video, write everything down that you can. And when we get to questions for the class, pause the video, try to work them out, then come back to the video just like we would do in class, where we take some time out to work on problems in class. Okay? So with that said, we finished chapter 25 before the break. And now we're going to move on to chapter 26 of Giancoli, which covers DC circuits. So let's get into that. And the first topic here expands a little bit on what we talked about in chapter 25 concerning batteries. Okay, so we're going to talk about internal resistance of a battery. So that just means the battery itself has some resistance to current flowing through it. EMF of a battery and terminal voltage of a battery. We're going to define all these terms and do a couple problems. So let's start with the definitions, okay? Ideally, when we think about a battery, we think of it as being a source of constant voltage. So maybe 12 volts across the terminal, 1 volt across the terminal, whatever the case may be. Ideally, we think of a battery as having a constant voltage across its terminals. But the reality is, that's not the case. The actual voltage across the terminals of a battery can change, and the reason for that is it has internal resistance. Okay, so resistance to current flowing, in the sense that we've been talking about before, is something that can happen inside of a battery. Okay? So we use the lowercase r variable to denote internal resistance of a battery, and internal resistance in a real battery is actually something that tends to increase over time as the electrodes are dissolved in the electrolyte solution. And as far as how you approach this in a practical sense, unless stated otherwise, we're going to ignore internal resistance in batteries, much like we ignore resistance in wires. Okay? But there will be some problems we do where we explicitly look at this idea of internal resistance, and we'll have to know how to deal with that. Okay, so that takes us to terminal voltage. Well, the terminal voltage of a battery, given by V, is just really the potential difference across the terminals. Again, if you go from the negative to the positive terminal of the battery, what is that potential difference? That's the terminal voltage. And then, what we call electromotive force, or EMF, given by the variable epsilon, this is just the terminal voltage across the battery when there is no current flowing through it. And as we're going to see, if there is current flowing through the battery, because of the internal resistance, the voltage can change a little bit. That's the idea. So let's take a look at a simple model of a battery. So if we look at the battery itself, we can think of it as having two components. There's an EMF. This is the voltage that drives current to flow when this battery is connected in a circuit. And then we have some internal resistance, okay, which impedes current from flowing. We can connect the battery to something, and in reality, this can be anything you want. It can be a light bulb, a motor, a heater, whatever the case may be. This is some kind of device that we connect the battery to, which has some kind of resistance. And we call that resistance the load resistance. And that's given by capital R. So it's just the resistance of whatever device, or even a set of devices that this thing is connected to. So let's take a look at terminal voltage to start off, okay? On my diagram, point A represents where you connect the negative terminal of the battery, and then point B represents where you'd be connecting the positive terminal of the battery. So VB minus VA, that potential difference is what we call the terminal voltage, because it's across the terminals of the battery. And so how do we calculate this? Well, the first thing to remember is that the way current flows in a circuit like this is you go off of the positive terminal of the battery, and then you loop all the way around to the negative terminal. So in this case, our current is going to be flowing clockwise, as shown in the diagram. And okay, let's go ahead and do the potential difference from A to B. So the first thing we do is we go across the EMF of the battery from the negative to the positive plate or terminal. And when we go from negative to positive, that's actually a voltage increase. So we have a positive sign, epsilon right here. And then we go across the internal resistance, which we just sort of conceptualize as a little resistor inside of the battery. And when we go with the current, okay, when we follow the current in this case, there's a voltage drop across the resistor, which is given by negative I times little r. So that's going to be the voltage, or the terminal voltage, when there's current flowing in our battery. But of course, what happens if we set I equal to 0? There's no current flowing. Well, then the terminal voltage is just equal to epsilon, which is what I was saying earlier. This is what epsilon represents. It's your terminal voltage when there's no current flowing. All right, so we have an example problem right here that I'd like to go over with you, and let's read it. We have an R equals 65 ohm load connected to the terminals of a battery whose EMF is 12 volts and internal resistance is 0.5 ohms. So we have a number of things to calculate here. The first one being, let's find the current in the circuit. Let's find I. Then let's find the terminal voltage across the terminals of the battery. And then we're going to find the power consumed by the load and the power consumed by the internal resistance of the battery. So we have 4 things to calculate, and let's get to it. So over here on the document cam, we're going to work this out. And I'm going to start by just copying down the circuit diagram that was shown earlier. So we have battery. Again, we can model this battery as 2 parts, an EMF, epsilon, and then an internal resistance, lowercase r. And that's connected like this to some kind of device which we call the load, given by big R. All right, so this is the positive terminal of the battery, this is the negative terminal, so we know which way current is flowing. It's flowing this way. That's clockwise. And on the diagram, what I'm going to do is label 2 points. Point B is up here, and then point A is down here. So the assumption we're making is that the wires that connect everything here have negligible resistance, so we don't have to think about that resistance. And if I'm trying to find the current, here's one way you can do that. Let's take the potential difference, VB minus VA. So starting at point A and then ending up at point B, what is the potential difference? Well, there are 2 ways to get it. One way goes across the battery, where we start with the EMF and then we go across the internal resistor, or we can go across the load, which is this way. And we should have the same potential difference because both are taking us from point A to point B, so we'd expect those to have the same value. So let's start by going across the battery. So the first thing we do is we go across the EMF from negative to positive. So we have epsilon. And then what we have is going across this little resistor R in the same direction that the current is flowing, so we have minus I times R. That's just Ohm's law, and then again, since we're going with the current, we have a negative voltage, or a voltage drop. We can also go this way, again across the load resistance, and if we go this way, we're actually going we're going against the current. Whenever we're going against the current, we have a positive voltage or a voltage increase, this time given by plus I times big R. So if you look at this equation I just wrote, it's going to help us solve for I, the current. Because if I rearrange this to say epsilon is equal to I times little r plus I times big R, if we solve for I, that's just epsilon divided by little r plus big R. That's the factor we get when we pull out I. Okay, so the numbers here are epsilon is 12 volts, and then the sum of these two resistances is we've got 65.0 ohms and then 0.5 ohms. But remember that an ohm is just a volt per amp in terms of units. So you do this calculation, and what you're going to end up getting is 0.1832 units or amps. But actually, what we want to do here is keep three significant figures. So we would round this off to 0.183 amps. That's the current flowing in the circuit. Okay, so the next thing we can do is calculate the terminal voltage, which is just the voltage across the battery, which is actually just VB minus VA. The very thing we were talking about up here. Well, as we said earlier, this is epsilon minus I times little r. And this is just telling us that, again, the voltage across the battery when there's current flowing through it, it's not actually 12 volts. It's a little bit less than that. It's going to be reduced by some amount. So we have 12.0 volts minus, take the current we just calculated, 0.1832 amps, and then take the resistance that's shown here, which is 0.5 ohms or volts per amp. So we're going to get some amount of volts here. And it turns out to be, rounding to the right number of sig figs, 11.9 volts. So a slightly smaller terminal voltage when we have current flowing. You can guess that if there's even more current flowing than that, then we have an even smaller terminal voltage. That's the idea. Okay, so the last two questions have to do with power. So we have two different resistors here in the circuit diagram. Again, one of these represents the internal resistance of the battery, whereas the other one represents the load resistance. And so each one of those is going to be consuming some amount of power, which is given by, if you remember, I squared R. That's the power consumed by a resistor. So we have to do this for two different parts. Let's start with the load resistance. How much power is that consuming? Well, we'll take the current that we found just a second ago, 0.1832 amps. We have to square that and then multiply by the load resistance, which is 65.0 ohms. And if you do the calculation, you get 2.18 watts. Okay? So that's the rate at which this load is consuming energy. If we do the same thing, but for the internal resistance, the calculation is I squared, but this time times little r, because there's a different amount of resistance here. So we have 0.1832 amps, square that, multiply by 0.5 ohms. And what does this work out to? Well, if you do the calculation, it's 0.02 watts. So if you compare the load to the internal resistance, this one is consuming much more power, which by the way is ideal, because this is where you want the energy to go, whatever device you connect it to. You don't want it to be wasted through internal resistance. Okay, so ideally this is really small and this is bigger. So that's the case here. All right, so normally I'd ask for questions, but if you do have questions about this, post them in the discussion board. So the next thing we'll do is move on to another example. Now this is a question for the class. So normally I would sort of pause things here, let you work on this with the people around you, walk around the room to help you with the problem. But instead, since we have the video format, what I want you to do is pause the video, try to work this out on your own, and then once you think you have an answer, come back to it, and then see if you were right. Okay? So the question here says, when a battery is connected to a load with resistance R equal to 465 ohms, the current that flows through the battery is 3 amps. When the same battery is connected to a load with R equals 559 ohms, the current flowing through the battery is 2.5 amps. So it makes sense conceptually that with more resistance, we're going to get less current. That should be kind of intuitive by now. But based on this data we have, we're going to calculate A, what is the EMF of the battery, and then B, what is the internal resistance of the battery. So that's what we have to do now. All right, so going back to the document cam here. We actually have some useful equations here from the previous example, and I'm actually going to write that down. From the previous example, we have epsilon minus I times little r equals I times big R. And I'm just going to rearrange that to say epsilon minus I times little r minus I times big R equals 0. So just subtract this term from both sides to get this. So if you think about it, we have two unknown quantities, epsilon and little r, the EMF and the internal resistance of the battery, which means we're going to need to generate two different equations. Well, the way we're going to generate these two equations is based on the data we were given. So we were told that when the load resistance, when big R, is equal to 465 ohms, the current flowing in the circuit is equal to 3.00 amps. So we can actually plug these numbers into the formula that we have here. So we have epsilon, don't know that, minus I, which is 3 amps, times little r, minus that same I, which is 3 amps, times big R, which we do know is 465 ohms, equals 0. So that's one equation we have. Let's call it equation 1. The second equation we can generate is when R is equal to the bigger resistance, which is 559 ohms. The current in that case is 2.5 amps. So again, take the equation here, just plug in the given values. We have epsilon minus 2.50 amps times little r minus 2.50 amps times big R, which in this case is 559 ohms. Okay, so that's equation number 2. So we have two equations, two unknowns. There are a number of ways we can go about solving the system, but I think the easiest thing to do in this case is just to take equation 1 minus equation 2. Just subtract one equation from the other. Okay, so let's do it term by term. First, we have epsilon minus epsilon. Okay, that's good because we basically just got rid of the epsilon factor. The next one is, let's write it down, minus 3 times R minus negative 2.5 times R. So basically overall we have minus 3 plus 2.5 times this little r. Okay, and then the last term is this. We've got minus 3 times 465 minus negative 2.5 times 559. So if I just group all of that together, that's minus 3 times 465 plus 2.5 times 559 equals 0. Okay, so it's pretty straightforward at this point just to get R. Let's work it out real quick. So when you combine what's in the parentheses here, you're going to get minus 0.5. And when you combine all of this in this other set of parentheses, what you're going to get is 2.5, and that equals 0. So R is equal to 2.5 divided by 0.5, i.e. it's just 5 ohms. So 5 ohms of internal resistance in this battery. So to get the EMF, we can actually just, again, use the equation we already wrote down. I can use equation 1 if I want to, plug in the internal resistance. I can use equation 2 if I want to, plug in the internal resistance. I'm going to get the same answer. So let's just pick an equation to use. How about we use equation 1? So I'm going to have epsilon minus 3 amps times 5.0 ohms minus 3 amps times 465 ohms. All of that equals 0. So basically, if you take these two negative terms, add them on both sides of the equation, you get epsilon equals 1410 volts. So that's the EMF. So admittedly, these are completely made up numbers. I'm not sure of a battery that exists out there that's exactly 1400 volts or around there. But again, this is how you solve a problem like this. All right, so moving on. That was kind of a short topic about batteries and EMFs and internal resistance. Hopefully you're now familiar with the terminology and how to do a basic problem. The next thing we're going to do is talk about resistors in series and parallel, and talk about something called equivalent resistance. Now back in chapter 24, we talked about capacitors in series and capacitors in parallel, and how to combine a whole network of capacitors into something called an equivalent capacitance. We're going to do something really similar here, except with resistors. How do I take some complex arrangement of resistors and simplify it into something that's a little bit more manageable? That's the idea here. So what I want you to think about is some kind of complicated network of resistors. They can be connected in any way you like, it doesn't really matter. But this network of resistors is connected to a battery that has a voltage V, and then as a result of connecting it to these resistors, there's some kind of current I flowing through it. Okay? Now, of course, I is just the current flowing through the battery. The current flowing through each individual resistor can be something else, but I just represents the current flowing through the battery. So if we want to simplify this situation, we can imagine that this entire network of resistors is actually just a single resistor whose resistance is Req. And if we connect that resistor to the battery, and we get the same exact amount of current flowing through it as before, that's called the equivalent resistance of this network, because it gives you the exact same amount of current as this network of resistors. That's why we call it the equivalent resistance. Okay? So how do we think about the equivalent resistance? Well, it's just Ohm's law. Battery voltage here is equal to I, the current flowing through this circuit, times R equivalent. So if we take the battery voltage and the current flowing through the battery, that sort of defines what the equivalent resistance is. So we're going to take a look at a couple different cases. First one is connecting resistors in series. Okay? So remember what it means to connect anything, any sort of set of devices in series. It means they're all connected along a single conducting path. So if current is going to flow through all of these resistors, it has to flow along one single conducting path. Okay? And that's what's being shown here. We have R1, R2, R3, really just any number of resistors, let's say the number is N, all the way out to Rn, connected in series, and then that's connected to a battery. That's what I want you to think about. So there are 2 points I want to make about this arrangement. And the first one has to do with current. Okay? This says when we have N resistors connected in series with a battery, the current through each of them equals the current flowing through the battery. And so what we have is I, the current flowing through the battery, is equal to I1, the current flowing through resistor number 1, is the same as I2, current flowing through this resistor, and so on, right? They're all the same current. The second point is the sum of the voltages across each resistor will equal the battery voltage. So in other words, if this is V battery, that equals V1, the voltage across the first resistor, plus V2, voltage across the second, plus V3, and so on. Those are 2 points I want you guys to understand. So let's go to the document cam and then work out why these 2 points are true. So right here we're talking about resistors in series. And the first point that I wanted to make about resistors in series concerned current. So why is it that all currents in that circuit you just saw are the same? And the reason is pretty simple, okay? Let's say the currents aren't the same. Let's say I have R1 right here and R2 right here. And then this is just some point in between them. So let's call that point P. Okay, let's say, just for the sake of argument, that I have 2 amps of current flowing through resistor number 1, but by the time I get to resistor number 2, I only have 1 amp of current. Okay, well, let's think about what that means for point P. At point P. So every second that passes, I'm going to have 2 coulombs of charge going into point P coming from resistor number 1. Okay? But every second that passes, I'm only going to have 1 coulomb of charge going away from point P towards resistor number 2. So if I take 2 coulombs minus 1 coulomb, I get 1 coulomb every second. That's actually building up at point P. And these numbers are totally arbitrary. But the point is, if these aren't the same exact current, you're going to have charge building up over time at point P, and that's just not what's happening in a circuit like this. This is just a point on a wire. There's no reason for charge to be building up here. Okay? So that's why all the currents are actually going to be the same. The other point was about voltage. Basically the fact that voltages, when we have resistors in series, are additive. Okay, so for this, actually I'm going to flip back to the slide real quick to show you something. So right here I have point A, and right here I have point B on the circuit diagram. The current is flowing this way, which is clockwise. So if I think about the potential difference between points A and B, so just go across the circuit in some path, starting at point A, ending up at point B, what's the potential difference? Well, there are 2 ways to go. One way is to go just across the battery. That takes me from point A to point B like this. And since I'm going from the negative to the positive terminal, that's a positive voltage. Okay? The other way I could go is like this, across all of the resistors. I'd have to go across all of them to get from point A to point B. And I'm going against the current, so I have a voltage increase, positive voltage here, across each one of these. Okay? So just by looking at the fact that when we go from A to B, it doesn't matter which path we take, we can see that the voltages are actually additive. Okay? So, thinking about that potential difference, VB minus VA, as we said, one way to get there is just to go across the battery, and that's it. We have V battery. But the other way to go involves taking the voltage across the first resistor, and then the voltage across the second resistor, and so on. I have to go across all of them until I get to the last one to complete that path. So that pretty much proves the point we were trying to make, that the voltages across the resistors add together to give you the battery voltage. Okay, and actually since we have that, let's do a few things with this. Let's make some substitutions. Now remember from before, the battery voltage can be thought of as I times the equivalent resistance. So I can sub that in right here. But the voltage across, let's say, resistor 1 is given by Ohm's law, I times R1. And we already established that all of these currents are exactly the same, so I'm just using I for any current that appears here. And then we have I times R2 for the voltage across the second one, and then you see this is going to be a big sum until I get to the last one. So how about we just drop the current out of this expression altogether to say that Req is equal to R1 plus R2 plus, you see where this is going, all the way to the last one. So that's my equivalent resistance for a bunch of resistors wired together in series. If I want to write this in a more compact way, summation It's the sum from I equals 1 to n of R sub I. Just add all of the resistances, you get the equivalent resistance. All right, so that was the last point I wanted to make, is that when we have resistors in series, the equivalent resistance is just the sum of all the individual ones. Okay, now actually, given something that we talked about back in chapter 25, I want you to see why this makes intuitive sense. We have this formula for the resistance of an object, which is given by R equals rho, which is called our resistivity, times the length of the object, divided by A, which is the cross-sectional area of that object. So I want you to think about what it looks like, how it changes the variables in this formula when we connect multiple resistors together in series. So the shape, the geometry really doesn't matter, but just so you have something to visualize, let's say they're cylindrical in shape, like this. Okay, so if I have one resistor here connected in series to another one here, think about which variable in the resistance formula we're effectively changing. Well, we're not changing the cross-sectional area, that's staying the same. What we are changing is the length. The total length of resistive material that the current actually has to move through now is greater that I've connected them in series. So we expect that if I do this, it's going to increase the resistance, right? If I have to move through a greater length of resistive material, I'm increasing the resistance. So that's why in our formula for REQ, equivalent resistance, that's actually a greater value for REQ than any individual R value, okay? So we're increasing the resistance. And that leads us to resistors in parallel, okay? So remember how parallel connections work. The idea here is, if we have a whole bunch of resistors connected in parallel, each one of them gets their own separate conducting path for charge to flow through. Okay, so I want you to imagine what's shown here. We have a battery connected in parallel to resistor number 1. That's connected to resistor number 2, resistor number 3, and then we can have any number you like. Just go all the way out to R sub n for these parallel connections. Now the first thing I want to make a point about is voltage. Okay? If we have resistors connected in parallel, the voltage across each resistor will be the same. Okay? Identical voltage across each one of these. And the easiest way to see that is actually just to look at, again, the potential difference between 2 points in the circuit diagram. So this is going to be point A, and this is going to be point B. There are many, many different paths we can take here to get from point A to point B, but remember, the potential difference isn't going to depend on which path we take. It's going to be the same regardless. So one path we can take starts right here at point A, goes across the battery, ends up here at point B. So what voltage are we talking about? The battery voltage. Another path I could take starts right here, goes across resistor R1, and then back here to point B. What voltage are we talking about? The voltage across resistor number 1. Okay, we can do that for resistor number 2, go across that one, get from point A to point B. So you can make that same argument for any one of these resistors. So the idea is the voltage across the battery is equal to V1, is equal to V2, is equal to V3, and so on. All the voltages are the same. So that's an important thing to remember when it comes to resistors wired together in parallel. The next point is about current. Okay? The sum of the currents through each resistor will equal the total current that's flowing through the battery. Now, the way you can see this is to think about the fact that charge is conserved. Okay? Whatever charge flows through the battery in a given amount of time is going to have to go somewhere. Well, it's going actually through a lot of different paths. It branches off. When we talk about I, it branches into I1, so some of the charge goes down this path, some of the charge goes down here to I2, some goes here to I3. So this total current just splits into I1, I2, I3, and so on. So we expect that if charge is conserved, I is equal to I1 plus I2 plus I3, and so on. So this total current through the battery is the sum of these individual currents. It's just a natural consequence of conservation of charge. All right, and then the last point here is about equivalent resistance. So let's derive that formula real quick. All right, so when it comes to equivalent resistance, okay, now we're talking about resistors in parallel. We know the voltages are the same, but how do I talk about any individual voltage? Let's say I want to talk about V1, for instance. Well, that's going to be given by Ohm's law. It's the current running through resistor number 1 multiplied by the resistance of that particular resistor. If I go ahead and solve for the current I1, well, that's going to be the voltage across resistor number 1 divided by R1. But actually, remember, all the voltages are the same, so I can just say this is the battery voltage divided by R1. Another thing to remember is that the whole definition of equivalent resistance is that your battery voltage is equal to the current flowing through the battery times Req. So I can actually solve for the current flowing through the battery, which we just call I. That's V battery divided by Req. All right, so the next thing I want to think about is, again, the fact that the currents add together. I is equal to I1 plus I2 plus ... all the way out to I sub n. So the next thing I'm going to do is just sub in for each one of these currents. For instance, I, current flowing through the battery, can be thought of as V battery divided by Req. We said over here that I1 can be thought of as V battery divided by R1. And you could have made that same argument for resistor number 2, right? That's just V battery divided by R2, and so on. And the last one would be V battery divided by R sub n. So why don't we just go ahead and cancel out all these V battery terms. Those just drop out. And what we're left with is our formula for equivalent resistance. 1 divided by Req is equal to 1 over R1 plus 1 over R2 plus ... 1 over R sub n. So this is how you do it for equivalent resistance when you have resistors in parallel. So at this point, I want you to look at our formulas for equivalent resistance for parallel and series, and it's the exact opposite of how it works for capacitors, if you remember. Remember, when we have capacitors in parallel, you just add all the C values. When you have capacitors in series, it's the inverse. Okay, so the rule for resistors and capacitors is basically flipped. Okay, really important to remember. All right, so the last point here was how do we calculate equivalent resistance? Well, it's like this. 1 over Req is equal to 1 over R1 plus 1 over R2, and so on. That's how it works. So with that said, we can do some examples. Actually, I forgot there's another slide here. Then an example. So I want to give you the intuition for why the equivalent resistance formula works out the way it does when we have resistors in parallel. So again, starting with the basic formula, that resistance is given by rho times L divided by A. So in this case, we want to think about when we combine resistors in parallel, which one of these variables that goes into the resistance is being changed here? Which one is being modified? Well, again, we're going to take the example of just two little cylindrical resistors connected in parallel like this. And so what are we changing? Well, we're not really changing the length. What we are changing is effectively the total cross-sectional area that the current has to move through, right? Let's say this area is the same as this one. It's double the area that the current has to move through when we have two of these. All right, well, if I increase A, I'm decreasing the resistance. So the equivalent resistance of anything wired like this in parallel is going to be less than any of the individual values. So we get less resistance when we wire things in parallel like this. All right, so yeah, here's the example I was thinking of. We have this network of resistors, okay? Each R value is the same, but some things here are connected in series, other things here are connected in parallel. Can we actually take this and then reduce it down into a single equivalent resistor? And what resistance does that have? So we're not going to put a number to this, we're just going to put some kind of numerical factor times R. So maybe it's a half of R, or like 20 times R. We want to figure that out given what we have here. So here's the process. I'm going to start by just copying this picture down, and then we're going to simplify things. We're going to find where we can combine resistors, then redraw the circuit. Combine some more stuff, redraw the circuit again, combine some more stuff, redraw the circuit again, until we just have one resistor left. That's the equivalent resistance. Okay. So we'll start with that same diagram we had up on the slide. So what did we have? We had point of connection here, and then we had a resistor R going across like this, resistor R going down like this, another point of connection here, resistor here, okay, another one going vertically like this, and then three more. One's up here, one's going vertically like this, and the other one is down here. So again, all of these R values are the same, so we'll just put R, R, keep writing R everywhere. Okay, so the question for us is, what are the first set of resistors that I can combine? Where you should be thinking of looking is right here at the rightmost part of the circuit, because clearly we have three different resistors, one here, and one here, which are in series, because they're connected along a single path. So we have to think about, again, let's say the rightmost three resistors, they're in series. So we have to think about what the rule is for combining resistors in series. Well, the rule is to just add them together. So the equivalent resistance of this set of three here is R plus R plus R. Just add them, which is 3R. So pretty simple. That's the equivalent resistance. The next thing we're going to do is redraw the circuit. Okay? So everything looks the same. Pretty much until we get to the right end of things. And now I just have a single resistor here in the rightmost branch of the circuit. So this is now 3R, as we just found. But everything else, we haven't combined it yet, so it's just R. So again, you look at the simplified circuit, and you think, what can I combine next? Well, the thing you should be thinking about is the rightmost two resistors. These are now in parallel. So how do we combine things in parallel? It's not just straight addition. Okay, so instead what we do is we say 1 divided by REQ is equal to 1 divided by R, that's this resistance here, plus 1 divided by 3R, that's this resistance right here. Okay, so basically what we have here is 1 over REQ. I want to combine these two fractions, so basically think of this as 1 or 3/3, and this is 1/3, so overall, what do we have? 4/3 with R on the bottom. I have to invert both sides of the expression here just to solve for REQ. So the equivalent resistance is 3/4 R. And again, it's time to redraw the circuit. So Again, the stuff here on the left looks the same. But now, we just have one resistor over here on the right. So let's label everything. We have R, we have R, we have R. But now this resistor here on the right is 3/4 R. So what's the next step we're going to take to combine things? Well, now we have a series connection again, where this resistor is in series with this, is in series with this, because again, they're all connected along the same path. So this would be the rightmost 3 resistors, which are in series. So let's get the equivalent resistance, Req. It's just the sum of those 3. So the first one right here is just R. The second one is 3/4 R. And then the last one is just R once again. Okay, so that's just some fraction. You can think of this as being 4/4, 4/4. This is also being 4/4. So overall what we have is 4 plus 3 plus 4, which is 11 divided by 4 times R. So 11/4 R is the equivalent resistance of these 3 in series. Okay, let's redraw the circuit one more time. And now what are we left with? Well, we have this resistor down here, which we haven't combined with anything yet. But we combined the other 3 to find that the equivalent resistance is equal to 11/4 R. So that's our circuit. So now we have a parallel connection between these two. So just apply the rule for resistors in parallel. So the remaining 2 are in parallel. And that means 1 divided by the equivalent resistance is equal to 1 divided by R for this one, plus 1 divided by 11/4 R for this one. So 1 divided by Req is equal to, here, let's write this as 1 over R. And then here what we have is 4 divided by 11R. That's effectively what that is. So 1 divided by Req, okay? You can think of the first one as being 11 divided by 11 plus 4 divided by 11. So that's going to be 11 plus 4 is 15 divided by 11 times R. And what we have to do to get our equivalent resistance is just flip that fraction, invert both sides, and that gives us 11R divided by 15. Okay. I was getting nervous, I was going to screw up the fractions, but that's the answer. Okay. So that's your equivalent resistance. It's actually less than any individual resistor. Again, that's not obvious until you go through the work of simplifying the circuit. So with that said, let's do another example. I want you to think about the idea of power output in this example. Okay, so we have 2 different circuits. They're both pretty simple. One of them is a battery connected to 2 resistors, which in this case, think of the resistors as being light bulbs, which can shine with a certain brightness. And in this case, they're connected in series. In this case, they're connected in parallel. So that's circuit 1, that's circuit 2. My question for you is, if we look at these 2 circuits and consider the fact that the battery voltages are the same, all the R values are the same, so they're identical light bulbs, how does the total power output of the bulbs compare in each of these circuits? Okay? So in other words, am I getting more total power output over here in circuit number 1? And that just quite literally means the bulbs will be brighter. Or am I getting more power output over here in circuit number 2? So again, what I want you to do is pause the video, see if you can work it out, then come back to it, and then we'll go over the answer. Okay, so welcome back. Let's go over the answer. What we're going to do is just make a straight calculation of the power output in both cases, and we're going to use this idea of equivalent resistance to help us out. Okay, so let's start with circuit number 1, which is the bulbs are connected in series, and think about what the equivalent resistance of the two bulbs connected in series would be. Well, remember the rule. If we have series resistors, the R values simply add together. So we have two factors, or two terms, R, that just add together. So 2R. It's double the resistance of one of the bulbs if they're in series. So effectively, our circuit now just looks like this. We have a battery, voltage V, and then you can just think of this as being a single equivalent resistor or a single equivalent light bulb connected to that battery, which has double the resistance. So of course we're going to get some current flowing in this if we connect a battery to a resistor in this sort of way, and it's going to be flowing clockwise off the positive terminal, looping back around to the negative. Alright, so if we want to know what the current is, we could use Ohm's law, because V is just equal to I times our equivalent resistance, which gives us the current equals V divided by our equivalent resistance. Do you guys remember how the power output of a resistor works? There are different formulas we could be using here, but the most straightforward way to do it, in my estimation, is just to say the power output is I squared times R. Yeah, that's how it works. And in this case, we're using Req because we have this equivalent resistance. So let's call this P1 total, the total power output of the light bulbs in circuit number 1. All right, so for the current, I can actually just plug in what I have right here, which is V divided by R equivalent. But that gets squared, the current is getting squared, and then multiply that by R equivalent. So overall on top we have a V squared, and on the bottom we have one factor of Req, because Req squared on the bottom times Req on top gives you Req on the bottom. And now let's just plug in our equivalent resistance. We have V squared divided by 2 times R. Or just think of this as a half V squared divided by R. So it's 1/2 of the voltage of the battery squared divided by one of the resistances. And so let's compare that to circuit number 2, which is in parallel. So the equivalent resistance for the parallel case, actually, let's write it this way. 1 divided by R equivalent is equal to 1 divided by R plus 1 divided by R. That's how I would get the equivalent resistance of two resistors wired in parallel, which is what's happening in circuit number 2. So 1 divided by R equivalent is equal to, well, combine these two terms, that's 2 divided by R, which means R equivalent, if you just invert both sides, is R divided by 2. So less resistance than any one individual resistor, as we said. And if we want the total power output of the two light bulbs in circuit number 2, it's just like before. We take V squared divided by Req. I'm not going to work that all out again, it's right up here. And in this case, we have V squared divided by R over 2. So it means this factor of 2 actually goes to the top. We have 2 times V squared over R. So it's pretty clear which one is giving us more power output. It's circuit number 2, where we have the bulbs wired in parallel. So if you want to get brighter light bulbs, it's better to wire them in parallel versus series. So to conclude, what we have is P2 total greater than P1 total by a factor of 4. So that's the answer. Okay. So now we're going to do yet another example. This one's really in-depth, using this idea of equivalent resistance. And before we dive into the specifics, the big picture is I've got some kind of circuit involving only resistors and batteries, and I'm going to solve for every single current in the circuit. All right, so consider the circuit shown above. The battery provides a voltage of 70 volts, and all resistors are identical. They all have the same resistance of 50 ohms. So we're going to do a couple of things here. We're going to first find the equivalent resistance of all five. We're going to use that to find the total current flowing through the battery. And then we're going to find the current flowing through each individual resistor. So we're going to have I1, I2, I3, I4, and I5. We're going to get all of that. So the first thing is to take the diagram that we already have with the 5 different resistors and label the different currents through the different resistors. Okay, so we have I1 going through resistor 1, we have I2 going through resistor 2, and so on. So each resistor gets its own current that's labeled on the diagram. And the first thing we should be thinking is, how can I combine any of these resistors? So take a look at the diagram for a second, and after you look at it for a while, it should hit you that the first thing we can do is combine R4 and R5 as a series combination. So 4 and 5 are in series. Okay, so there are two things I know given that they're in series. The first is, remember, any two resistors in series have the same current. So I4 and I5, those aren't two separate currents, they're the same thing. And I'm going to call that I45. So it's just the current that's common to these two. That's the notation. And if I want to combine them as a single resistor, well, I'll call that R45. And all I have to do is add R4 and R5. Just add those together, get the equivalent resistance. So again, if we plug in the numbers, each individual R value is 50 ohms. So 50 plus 50. Effectively, you just have an 100 ohm resistor right here on the right branch of the circuit. So the next thing is redraw. So everything looks the same, except now I've combined 4 and 5 as a series combination right here, and the current flowing through that I'm calling I45. All right, so the next thing is, look at this diagram, try to think about what can be combined using the rules for series or parallel capacitors, or resistors, sorry. So we have actually 3. There's R2, there is R3, and then there's R45. This is one big parallel combination. Okay, so now we have to think about what we know about parallel combinations. So there are a few different things. The first is that the voltage across this, and this are identical. Okay, that's one fact we know about parallel resistors. So we have V2 equals V3 equals V45. Those are all the same voltage. But currents, they work a little bit differently. So the way currents work when you have resistors in parallel is that they add together. So if I have some kind of total current flowing through all 3 of these, and we're going to call that I2, 3, 4, 5. Now it's getting a little heavy with the notation, but it's the combined current of all of these. That's just going to be I2 plus I3 plus I45. In other words, these just add together to give you the total current. Now for the equivalent resistance of this set of 3, we have to use the rule for parallel. So we have 1 over R2, 3, 4, 5. So that's the combination we want to make. Is equal to 1 over R2 plus 1 over R3 plus 1 over R45. And just to save time, if I want to solve for this, just invert both sides. Okay? So on the left, we just have the resistance we're looking for, and on the other side, we have this big sum to the -1 power. Just think of it that way. So now we'll put in the numbers. Well, R2 is 50, R3 is also 50, but this equivalent resistance of 4 and 5 is 100. So it's 1 over 50 plus 1 over 50 plus 1 over 100 all to the minus 1 power. That's the calculation. And so, okay, 1 over 50 is 2 over 100, so think of this as 2 plus 1 all over 100. So that's 5 over 100. To the minus 1 power, it's going to give us 100 over 5, which is 20 ohms. So that's the equivalent resistance of 2 through 5. We've almost combined everything. Okay, so what do we have when we redraw the circuit? Well, now what we have is R1, which we haven't dealt with yet, in series with R2, 3, 4, 5, when we combine all of these together. And the current that's running through this equivalent resistor is what we call I2, 3, 4, 5. Okay, so we'll keep going. That's the picture we have. Okay, just basically 2 resistors in series connected to a battery. And let's combine the last 2. So we have R1, R2, 3, 4, 5, and the battery all connected in series. So we know a couple of things. I, which represents just the current flowing through the battery, is the same as I1, is the same as this current, I2, 3, 4, 5. Same current everywhere. It's just one continuous loop. As far as the equivalent resistance goes, when we actually combine all 5, so R1, 2, 3, 4, 5, that's this resistance plus this resistance. Okay? Just add those 2 together. And so R1 is 50 ohms. R2, 3, 4, 5, which we just found is 20 ohms. So add those together, what do we get? 70 ohms. So the equivalent resistance of everything is 70 ohms. And here's our most simplified circuit. Okay, it's just, we've got a battery, some kind of current flowing through it, connected to an equivalent resistance Req. So that's what we have. And if we want to get the current flowing through the battery, just use Ohm's law. That voltage is equal to I times Req. Pretty simple. Go ahead and solve for I. That's V divided by Req. And we'll put in what we know. So I wrote this problem to make the numbers come out nice and round. If you remember, the voltage of the battery was 70 volts. We found 70 ohms for the equivalent resistance, so you actually get exactly 1 amp of current flowing through the battery. Okay? So we've answered 2 of the questions. We have the equivalent resistance, we have the total current flowing through the battery, but now what we have to do is find the individual currents. So we've sort of simplified everything as much as we can. We wrote down some equations along the way. Now we're going to start using those equations that we wrote down as we got here to solve for the individual currents. All right, so the first thing is just what we set up here. There's the same exact amount of current flowing through the battery as there is through resistor 1, as there is through this combination over here of 2, 3, 4, and 5. So the current I1 is the same as the current I2, 3, 4, 5, which is 1 amp, what we just found. So we actually figured out what the answer is for resistor number 1. It's 1 amp. Now, if we want to get the other ones, one thing we should be thinking about is how parallel resistors work. We talked about the fact that 2, 3, and the 4, 5 combination are all together in parallel, which means they have the same voltage. And the voltage across a resistor is just I times R. It's the current times the resistance. So that means we have, for V2, I2 times R2. For V3, we have I3 times R3. And for the last one, we have I45 times R45. So that's one, actually, set of equations we have. And let's work with that for a little bit. So for now, just look at this equation right here, relating to 2 and 3. If I go ahead and divide out R3, I'm going to solve for I3, which is R2 divided by R3 times I2 is equal to I3. Another thing I can do is plug in the numbers. Well, 2 and 3 have the exact same resistance, so this just leaves you with I3 and I2 are the same. Same current for 3 and 2. That's useful to know. Okay, another thing we can do is look at these two, compare the voltage across 2 to the voltage across the 4 or 5 combination, and actually solve for I45. So that means we're going to divide out this R value right here. This says I45 is equal to R2 divided by R45 times I2. And we know what those values are. From before, well, R2 is just 50, that's just one individual resistor, and then 4 and 5 together have a resistance of 100 ohms. So this is like 50 over 100 times I2. Or we could just say it's a half times I2. Okay, the next equation that we came up with along the way was also about this parallel set of resistors, but it was about how the currents add together. I2, 3, 4, 5, that total current through that combination of resistors, is equal to I2 plus I3 plus I45. Remember, the currents add when you're in parallel. We already came up with this. So what I'm going to do with this now is make some substitutions. Because from up here, we said I3 is the same exact thing as I2. So just sub in I2 for that. We also said I45 is a half of I2. So put that in right here. Now this is useful because basically I have 1 plus 1 plus a half, or 5 halves times I2, if you look at what we have over here, equals I2, 3, 4, 5. So go ahead and solve for I2. That's going to be 2/5 times I2, 3, 4, 5. We know this current right here, so plug it in. Remember, that was 1 amp. We already came up with that. So I2 is 2/5 times 1 amp, so 0.4 amps. All right. Now let's look at I45. Okay, what's the current through resistors 4 and 5? Well, we already said up here it's a half of I2, so if I2 is 0.4, this is going to be a half of 0.4, or 0.2 amps. And that actually solves the entire circuit because, okay, equivalent resistance of 70 ohms, current flowing through the battery is 1 amp. The current through the first resistor is 1 amp also. 2 and 3 we said were the same, and we got 0.4 for that. And then 4 and 5 are also the same, we got 0.2 for that. So that's how you solve the circuit using these rules of equivalent resistance. That's how it works. All right, so that was kind of a long example. I'm going to give you guys one to work on. It's a question for the class. And I think after we do this one, we can just call it a day. So in this one, we have a circuit with 3 different resistors and 1 battery. That's shown right here. Now the resistances are as follows. We have R1 is equal to 400 ohms, R2 is equal to 500 ohms, and then R3 is equal to 700 ohms. And then the battery's terminal voltage is going to be 12 volts. All right, so basically, it's the same exact sort of question. We're going to find the equivalent resistance, and then we're going to find the current flowing through each individual resistor. So it's really the same kind of problem that we just did, but sort of a different circuit. All right, so again, pause the video, see if you can get this, and then come back. And here we go. Let's work it out. So I'm going to start by copying down the circuit that we have. We have a battery with some kind of terminal voltage V, positive, negative terminal. Then we have R1 right here. And then that's connected to R2 and R3 like this. So I have R3 down here, R2 up here, and then R1 to the left. And then this wire comes back around to connect this whole thing in a circuit. Okay. So the first thing we should do is label each current that we're trying to find. So the current across resistor number 1, we can call that I1. current across resistor number 2, that's going to be I2. And then current across resistor number 3, that's I3. Okay, so the first thing we should think about is what kind of combinations can we make here? Well, most obvious thing to do is just take 2 and 3 and connect them as a parallel combination. So 2 and 3 are in parallel. So let's write that down, 2, 3 in parallel. And that means there's an equivalent resistance, let's call that R23. 1 over R23 is going to be 1 over R2 plus 1 over R3. And what we're solving for is R23. So invert both sides. That's going to be 1 over R2 plus 1 over R3 to the minus 1 power. So let's calculate that. R23 is going to be 1 over 500. That's the value of R2 we're given, plus 1 over 700, and then take that to the minus 1 power. When you do this calculation, you're going to end up with 291.67 ohms, and technically we'd want to keep 4 sig figs on that. All right? So before we move on to the next thing, let's just think about whether there's anything else we can say or any other equation we can write down given the fact that these two are in parallel. And yeah, there are a few other things we can say. So this was the equivalent resistance right here. When it comes to voltages, well, the voltages are the same for 2 and 3. So in other words, V2 equals V3, which means I2 times R2 is equal to I3 times R3. Again, just using Ohm's law here. And this is useful because I can sub out one of the currents. Let's say I'm going to sub out I3. I'm going to get rid of that. So I3 is equal to I2 times R2 over R3. Or in other words, it's 500 over 700, that's the ratio of those two resistances, times I2. 5 over 7 as a decimal, that's going to be 0.71429 I2. I'm keeping those 4 sig figs once again. Okay, the last thing we can say about these two resistors that are in parallel is that the currents add together. So in other words, call this I23. The total current running through both of these together is equal to I2 plus I3. All right. Next thing to do is redraw the circuit. So when we redraw the circuit, we see that we have a battery connected to R1, connected in series now to R23. So now our circuit is kind of simple. It's just one big loop. And let me label each current that's relevant here. So we have I1, it's current flowing through this guy. We have I23, the current flowing through this combined resistance here. And actually it's useful to label what we call just I, the current flowing through the battery. Okay? So the first thing to note is what we have is a series combination of a couple different things. We have the battery, we have resistor 1, and then the combined resistor R23. That's all in series. So one thing we can say about series combinations like this is that the currents are equal. Currents are the same. So that means I, the current going through the battery, is the same as I1, is the same as I23. Those are all the same thing. Now let's do the equivalent resistance. So that would be R1, 2, 3. We've combined all three. Well, since they're in series, this just means they add together. R1 adds right to R2, 3. So we can actually plug the numbers in and get the answer out. This is going to be 400 ohms for R1, added to 291.67 ohms, which we found earlier is R2, 3, giving us an equivalent resistance of 691.67 ohms. And to the correct number of sig figs, which I guess would be 4 here, is 691.7 ohms. So equivalent resistance for the entire circuit has been found. So I guess we could just redraw this one more time. And now what we have, since we've combined all of the resistors into one equivalent resistance, is just a battery connected to REQ. Nothing more than that, and then some current flowing in the circuit. So, simplest possible circuit you can have. And so if I want to get the current right there, I'm going to use Ohm's law. V is equal to I times REQ. And then the current is going to be V divided by REQ. So what was the voltage? I almost forgot. 12 volts. Yeah, 12.0 volts divided by the equivalent resistance, which is going to be 691.7. Let's actually say 67 ohms, which is a volt per amp. Okay, so we get the current I, which is 0.017349 amps. But in this case, we should actually be keeping just 3 sig figs from up here. So the answer I would write here is 0.0173 amps. So that's the current flowing through battery. But we just said a second ago that the current flowing through the battery is the same as the current flowing through R1, is the same as the current flowing through this 2-3 combination, so let's write that down. I1 is equal to 0.0173 amps. So we know that right off the bat. And now we have 2 more currents to figure out. So I23 is the same thing. Let's write that down. Okay, so the remaining currents to find are I2 and I3. So just to remind you, those are the individual currents flowing through resistors 2 and 3. All right. So I have some equations that we already wrote down that I'm just going to call back to. And the first one is this. I23 is equal to I2 plus I3. So that was for the parallel combination, just the statement that the currents add together. What else did we have? Well, up here, we said that I3 is just equal to this factor times I2. So let's take that all together. I23 is equal to 0.017349 amps. That's equal to I2 plus I3. So we'll write I2 right there. But I3, again, we can sub out for I3 0.71429 times I2. Okay, so we're almost there. 0.017349 amps equals, what we have here is just, if we add 1 to this decimal, 1.714 1.1429 times I2. Okay, so all we have to do to get I2 is divide this number by this number. So let's do that. I2 is equal to, when you do the division, 0.0102, sorry, let me erase that. Let's write that again. 0.01012 amps, which we'd have to keep 3 sig figs here, so we'd have 0.0101 amps. Okay, that's I2 right there. The last thing to do, and I'm just running out of space, is to find I3. But again, I3 is nothing more than 0.71429 times I2. So let's take 0.71429 and multiply by what we just found for I2, which is 0.0101 2 amps. Okay, do the multiplication. And look, we know we're going to round off to 3 sig figs at the end of this, so let's just do that. We have 0.000723 amps. So that's I3. So to summarize, I1, what we got was 0.0173 amps. I2, what we got was 0.0101 amps. And then I3, what we just found here is 0.000723 amps. Those are the currents. And again, we can find these currents by using the rules of equivalent resistance. So we're going to end it here, but next time we're going to learn about some other rules that you can use to analyze a circuit, and they're called Kirchhoff's rules. And in some ways, it's a lot more efficient and less messy than what we're doing here, so you might like it a little better. But it is good to know both ways of doing it. And then after that, the lecture after the next one, we're going to talk about something called RC circuits. So that's it for today. Again, everyone out there, stay safe and healthy, and I'll see you next time.